or 6364. So we're going to start off with the nature of energy. As it turns out, when you take a look at this, this is called an emission spectrum, or actually we're going to actually do something with this. This is a spectrum picture of a gas. It's neon gas, and when you apply a high voltage electricity, it forces the atoms, the electrons in the atoms, to jump up out into an excited state, and when it jumps back down, it gives off a specific wavelength of light, which is what you're looking at here. That's the orange color. So this is a neon light. I know you've heard of neon lights before. That's because they were it's one of the brightest gases to first be discovered to give off a light when you put a lot of energy to it, like electricity. So let's continue on. So there we go. So let's talk about the nature of energy. One does not observe. So if you shine a bright white light through a prism, what you will get is on this side over here, you will get what's called a full line spectrum, which means that all the wavelengths, it's called a continuous spectrum, which means that all the wavelengths are represented in visible light. And what you'll see then is the rainbow color, so Roy G. Biv. But if you do this prism, if you shine a light through the prism, but that light comes from like the neon gas, then only specific wavelengths are given off by that light, so you will not see a continuous spectrum like we have up here in the corner. What you'll see is something called a line spectrum. So only a line spectrum comes from discrete wavelengths is observed. That doesn't really mean much to you, but here is hydrogen. Hydrogen has, it's tough to see, but it's got a couple of wavelengths, so it's really tough to see, that you can see here and here. And hydrogen has like a color to it, almost like a bluish color that you'll get to see in the lab unless you're an online student. Sodium is like a bright yellow light, and one of the reasons why it's a bright yellow is because of that line right there. Notice most of the spectrum here is blank. So if we're comparing the continuous spectrum up here to a line spectrum, the lines like they only take up a very small wavelength of light compared to the continuous spectrum. So let's keep going here. So what's happening? Well, here's what's going on. When we force a lot of electricity through a gas at low pressure, the electrons for the atom, they jump up. So some may be jumping up from the first main energy level. So this all the way down here. And by the way, down here would be down here where the nucleus is. So the nucleus is down here with the protons and neutrons. And what happens is the electrons start off here, and then they get forced way up. And then they stop here. And then when they jump back down, they give off this amount of light. Okay, so now here's the cool part about this. The electrons don't just like bump up and come back down. There are places for the electrons to go that they can only go to. So don't think of this like an inclined plane where the electron gets bumped up to here and then it jumps back down like that. Think of this like stair steps. And when we walk up stair steps, the electron gets bumped up to here, and you can't step in between the steps, right? So there's only like there is no, you do one step at a time, and there is no in between the steps on the stairs. So that's what happens to the electron. These places that you're looking at here, 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 these are all places like stair steps that the electrons can fit into, and then when they back down again, they give off a very specific wavelength of light, because this distance represents a certain amount of energy, okay, from one stair step to the next. So like each one of these has a certain amount of, each one of the steps that I'm looking at right here has a certain amount of energy, and this would be like 3 steps. That would be the energy of this electron when it jumps back down to give off 3 steps worth of energy. So that's exactly what's happening over here on the right-hand side. It says electrons in an atom can only occupy certain orbitals, okay, or steps. Orbitals and steps are basically the same thing that we're talking about here. I'm erasing this so it doesn't get too confusing. So corresponding to certain energies. So if you're going from step 1 to step 2, or orbital 1 to orbital 2, or actually this is main energy level 1 to main energy level 2, every time that electron jumps back down to main energy level 1, it gives off exactly the same wavelength of light each time, which is why when we take a look back here, which is why there are only certain wavelengths that I have circled here. So when you take a look at these line spectrums, sodium atom has like a very specific pattern where the electrons jump up and jump back down and give off that wavelength, okay? And only that wavelength, which is because it goes up to a certain step and then jumps back down. Okay, so let's keep going so I don't take too long. That's what I was trying to show you here. Down at this step here, this is the nucleus. Like that, we can have our first step, which is called n equals 1, n equals 2, bonehead, n equals 3. In actuality, and these steps are way more complicated than what you're looking at, but in actuality, this goes all the way up to step 7. So we have n equals 4, and then it would be n equals 5, n equals 6, and then n equals 7 is our last step. So these are the places that the electrons can sit. The major energy level, or the main place outside the nucleus, there are 7 of them, and that's our introduction to what the outside the nucleus looks like for an atom. Let me see what else we got here. Come on. There we go. So Niels Bohr adopted the Planck's assumption and explained these phenomena in this way. He said electrons are permitted orbits, or specific allowed energies. These energies will not be radiated from the atom. So that's just Bohr talk. Don't worry about that. Basically what he said is the energy is absorbed or emitted in such a way that to move the electron from one allowed energy state to another. And he uses this formula, energy equals Planck's constant times frequency. So when we plug in a whole bunch of math stuff that we're not going to have to do, at least not right away, notice that you got the minus 1/4 and then HCR. R stands for Rydberg constant. Rydberg constant is part of the math that we're going to talk about. So the further away you get, well, we'll talk more about that math stuff. That's not a main focus of mine. What I'd like to focus on is the fact that you have a principal quantum number, or a main energy level 1 here, and then a 2 here, and then 3, and then 4, 5, 6, and then it says it goes to infinity. By the time the electron gets that far away to right here, then it's so far away that it's not particularly feeling the effects of the nucleus anymore, where they're attracted to each other. Remember, the nucleus is protons and neutrons, which means an overall positive charge, and the electrons are negative, which means they attract each other. Okay, so there's more talk about this. So the difference between the energy levels has an energy value. We're not going to get into what all of this means. It's not that difficult. This right here is this number, okay, and the number of joules. It's 1 over the n right here. That F means final, and the I here means initial. So if you start off in 1, this would be 1 over 1 squared. This one, it would look like this. If you went from energy level 1 right here to energy level 2, this would be your N initial, this would be your NF. Okay, so that would be 1 over 2 squared minus 1 over 1 squared, like that. So that would be, of course, 1/4 minus 1, which would be a negative then, negative 3/4, or a negative 0.25. And then you would multiply that by that term, the Rydberg constant. Okay, not important. I just want to show you how easy it was, though. It's an easy thing to do, so you can go from any one of these steps to any other steps. Unfortunately, though, that only works for the hydrogen atom, because as soon as you put in other electrons, things start getting a little wonky. So Heisenberg, came up with this thing. I may have gone too far. I'm not sure. Let me just check to see. Yep, okay. So the last thing in 6.4 and 6.5 is, or 6.3, 6.4, is the uncertainty principle. So I just showed you how the electrons can jump up and jump back down, and they were very interested in knowing more precisely the momentum of the electron, to know where it is and to know what it's doing, but it was moving so fast and it's so small that it's difficult to predict where it's going to be and what it's doing. So Heisenberg said, yeah, you can't know how fast it's going and in what direction, and also know its mass at the same time. So fast and direction and mass is called momentum. And so it's just one of those things where you're saying actually the amount of uncertainty is actually larger than the atom itself. So this was what he did basically was put a limit. No matter how accurate you have of a measuring tool, there will always be some uncertainty to it. And in this case, the uncertainty is usually larger than the atom itself, which poses a problem. So that was one of the things that they were trying to solve at the time. So make sure you get some of the notes about this. We'll talk more about the uncertainty principle later on. And that's it for 6.3, 6.4.